Recording is on, second half, November 4th, Math 4707. We are in the midst of proving Kirchhoff's matrix tree theorem. And we've gotten to the most interesting part, the one that finally uses some matrix linear algebra. And let's do it. So what we've said is we're trying to show that we start out with a graph G. Here it is. We're assuming that the vertex V, where we've reduced its Laplacian matrix. Let's draw its Laplacian matrix. Let me draw it right here. And we'll even draw it with the reduction. So we'll put in 1, 2, 3, 4 is V. And 1, 2, 3, 4. So that's again the V. And sorry, I've got my view options such that I can't see what you can see. Here we go. All right. And so let's put in the Laplacian matrix entries. So they are, okay, vertex 1 has degree 3, vertex 2 has degree 2, vertex 3 has degree 3, and vertex 4 has degree 3. No, vertex 3 has degree 4. Wow. All right, let me put them in. On the diagonal, I've got a 3, a 2, a 4, and a 3, I think, for the diagonal entries. And let me put in the off-diagonal entries. What do we got? Let's see, 1, 2, there's a negative 1. 1, 3, I've got a negative 1. 1, 4, no, yeah, 1, 3 was a negative 1. Stop me if I make a mistake, please. 1, 4 is a negative 1. Let's see, 2, 3 is a negative 1. And 3, 4 is a negative 2, is that right? Who am I missing? 2, 4 is a 0, right? Anybody feel like I wrote down the correct Laplacian matrix there? Any errors? Okay. Good. And let's do the reduction. Let me emphasize the part that's not reduced. So I deliberately put the V in the last column so that this submatrix would be the part after we reduce. Maybe I'll sort of lightly do the striking out here. We're going to be striking out that row and column for this reduced Laplacian matrix. Everybody good? So that's the 3 by 3 determinant that's supposed to compute the number of spanning trees here. I'm not going to compute it. We're just going to explain the relationship between these three matrices. All right. So because we chose V was not an isolated vertex, we said there was at least one edge E, and we just picked one. It was incident to V. And then I said we should name the other vertex on the other end of that edge E, let's call it W. So I never labeled that here, but let's call that thing W. Once we pick the E, I have no choice about who W is. But I was actually smart enough when I did this. Okay, I guess because I had it in my notes. Whoop. Let me steal this matrix here. I was smart enough to put the W in the second to last column. Not that it matters. I just, you can label it however you feel like. And now let's compute first of all, what is G with E deleted? Well, that I should be able to draw in my usual sneaky fashion by copying and deleting the edge E. All right, so I want to do G with E deleted. And so I blow this up a little bit and I take out edge E. It's gone. Good. All right. And then let's also draw G with E contracted. And this is the one where I have to squish together vertices 3, 4 to make the super vertex 34, which is really my vertex VW. So let me do that. I've got the 1, the 2, the VW, the 3, 4 is VW. And what's going to be labeling these things? Okay, from 1 to 2, I've still got the A. From 1 to 3, 4, I had a B, and a C, right? And from 2 to 3, I've got a D. And I've got a loop F there that's on vertex 3, 4. Does it look like I've drawn that right? I think it's okay. I'm looking at my notes and it looks similar to what I have drawn in my notes. Okay. But now what I'm going to do is carefully draw the Laplacian matrix for G with E removed. And in columns 1, 2, and 3, right, where you're avoiding the vertex V that that E was incident to, I claim it's going to look exactly the same, right? Even though vertex 3, right, is W, the thing that was connected to E, because these are all vertices that have nothing to do with V. What's going on in these first 3 columns, that edge E never contributed to any of it, except, okay, I lied a little bit. There's one place where it contributes. This 4, which was the old valence for vertex W, for vertex 3, now it has one fewer edge. That's going to change to a 3, and the rest of this stuff looks exactly the same. So what am I claiming? That this stuff is in the part that we are not striking out. Whoop, didn't mean to do that. That's the V. That's the V down there. That all these entries up here, they look almost exactly the same as this matrix. The one thing is that the valence of W went down because we removed the edge E that was incident to W. Everybody okay with that? So let me emphasize the difference there, because that's going to be a key point. Let me just circle that 4 went down by 1 to turn into a 3. Okay? Good. And now, since I'm going to strike them out, it actually doesn't really matter what entries I put here, but you know, we can put them in. It's not so important. I'll list them, but we're not going to pay a lot of attention to them later. No, that's something that changed. Yeah, that entry actually went down by 1 also. And vertex V also, yeah, its degree went down by 1, but I'm not so concerned about that because we're striking that out when we compute the determinant. Since I chose to reduce this one, oops, what am I supposed to be drawing for you? I was drawing for you the reduced Laplacian for the deletion of edge E, and I was reducing it at vertex V. Everybody okay with that? All right, so it's the stuff in the upper left. It's the stuff that's up here. Now let's do the G mod E, its reduced Laplacian. So reduced Laplacian for G mod E, and I'm going to reduce it at VW, which is our super vertex VW, the one that's 34 in this picture here. So that one's a little smaller. It's, before I do any reduction, it would be 1, 2, and then the 34, which is the VW. 34 is VW. But what I claim is, if I look at its little upper 2 by 2 here, but what does that mean? Look at the vertices that are neither V nor W. Like everybody except for the VW rows and columns, that little blue matrix that's now 2 by 2, it looks exactly the same as in here and in here. So let me mark it off in here, and here. When we focus on vertices that are neither V nor W, all those entries look exactly the same, whether we were in G or G with E removed, or G with E contracted, right? What am I saying? For the vertices that are not V or W, their valence is the same because they don't involve that edge E that we contracted. And the number of edges between them is the same because it's not E. E is not between them. Does everybody see why this upper left blue thing that has to do with the vertices not V and W looks exactly the same in all three matrices? Good. And now I can carefully write down what these entries are, but we're going to be striking them out anyway. Still, let's write them down. It doesn't matter. I'm just going to write them from my notes, and you can check me that I didn't get them wrong. Okay, so there's something, but they're going to be struck out. So I strike them out. Theo says, wait. Go ahead, think, Theo. Yeah, I'm happy to wait. Isn't the corner one a 4, you say? You're talking about this one, this thing that was that I wrote 3. Yeah, self loops don't count. That's right. I could remove the self loops. They show up when you do deletion and contraction, but when we write down Laplacian matrices, they don't count toward the degree, just like they don't count toward the number of spanning trees. Yeah, good question. Okay. And so now let's think about it. The claim is this is actually enough to show that the determinant of this one on the left is equal to the determinant of this one here on the right plus this one here on the right. In other words, I'm claiming if we think about this, the structures that we just talked about, the fact that the orange things only differ in that entry right there going down by 1, and that these blue things are exactly the same in all 3 will show us this relationship. We just have to remember how you compute determinants. And so I recommend that we pause for a moment. Nobody say anything. So let's think about it. How could I compute this determinant in such a way as to convince myself that it is equal to this determinant plus this determinant? That's what I want to do. I want to compute this one a certain way. Don't say anything, nothing in the chat. Okay. All right. Anybody, you can write in the chat if you think you understand why that would be. Anybody see why? And Theo saying row expansion, last row. Whoa, a lot of stuff written in the chat. Which row, column, yeah. Right, that'll work, I agree. So let's write that. There's a little more to say. I'll call it Laplace expansion. That's what people sometimes call this, Laplace expansion along the last row or the last column. It doesn't matter, it's a symmetric matrix. Yes, so yeah, Theo, do you want to unmute yourself? Are you capable of muting yourself? No, okay, but I'll read what you wrote. I think that's right. Vacuum's running, good. I don't want to hear your vacuum, I agree. So, right, what happens if we compute this, right? It's this orange upper left matrix we're supposed to compute. When we compute it by expanding along the last row, right, you get these entries times their cofactors, where you strike them out, their row and column, things like this. And the point is, they all look exactly the same, except when you get to that last entry in the row. Then its cofactor is the blue thing, right? And in this one, same story, its cofactor is the blue thing. It's just here you've got the number in front of the blue thing is one bigger than it was here. Oh, but you're adding the blue thing there. Everybody get that? The point is, the difference between the row expansion along the last row for this one, this determinant, is that you get 1 times the blue cofactor more than you would here, because this number was 1 smaller. But then this fixes it. Sound okay? All right, so let me just say, because of the difference by 1 in the green circled entries, namely the diagonal at W. WW. Okay, I'm gonna say, I think I proved it. At least I intimidated you. No, but seriously, think about it. If you have questions, I'm happy to explain it more in office hours some other day. Just ask me about it. Good. I think we got Kirchhoff proven. Questions before we move on to next topic? Okay. Yeah, so what's our next topic is, I think I had already told you what the next topic was going to be, but let me remind you, it's this minimum cost spanning trees. Oops, spanning trees. And this one really comes up. It's one of these algorithms that works so well, surprisingly well and fast, that it gets used as a precursor for other algorithms. People know it's like, oh yeah, that one we can solve. So maybe we can reduce our other problems to solving this one. So how does it work? We're going to give the edges. If the edges of our graph G are given costs, assigned costs. Yeah, let's just call them cost of E. Okay, the edge is E. Then the question is, how can we find a spanning tree? In other words, a set of edges that connects all of the vertices in the graph, sorry, all the vertices in V at minimum cost. Let me write it like this: a subset of edges that connect the vertices with the minimum cost. Minimum total cost. Am I going to name, and maybe later I will name that, but now let's do it now. Let's call it cost of T. And I just mean the sum of the costs of all the edges that you used. Okay, so the first thing we want to realize is, I didn't say the word tree in this first paragraph here, but it will be a spanning tree. Note that T must be a spanning tree. Because yeah, why must it be a spanning tree? Let's think about it. Let's have an example in mind. Same example that I drew earlier. I think I'd drawn you some picture like where I had this graph, these multi-edges, these costs, right? And we decided that the minimum cost spanning tree was that one, and its cost is 3 plus 5 is 8. But it has to be a spanning tree because if it had any cycles, right, you could remove an edge and it would still connect all the vertices and it would lower the cost. Right, so this is this property that we saw for spanning trees. One way of saying you have a tree is that it's acyclic and, sorry, not that it's acyclic, that it's connected and it's minimally connected, right? Trees are the minimum, the graphs which are connected, and removing any vertex disconnects them, okay?
We have negative cost edges. Well, I guess you just add in all the negative ones because
this is actually an important point. Let me say that explicitly. You're right, William. If we had negative costs, then that would not be allowed. So yeah, costs greater than or equal to 0.
But I guess if you have any negative costs, you just ignore them for a bit, then you add them in at the end.
Yeah, the issue, of course, is that what if you needed those negative cost edges to actually connect the graph, right? If any of them were necessary for keeping the graph connected, you're in trouble, right? So I guess you're right. We could just keep them for the end. I guess it's still okay. I have to think about that, actually, how you modify the algorithm. In some sense, you can just take the biggest of the negative costs and just add that to everyone. Will that work? I think that'll work to make everybody have non-negative cost. Yeah. Anyway, we'll think about that. So
you don't ignore them. You just do it normally, just treating it completely normally, and then at the end you add in any extra negative edges you have left, because then you don't have any positive edges standing in for negative edges. Like that, I think.
Let me think about it later. Okay. All right. So T is going to have to be a spanning tree in G. It might not be unique. There's nothing that says there's always a unique minimum cost set of edges. Just to give another example, right? If I had given you the same graph, same structure of the edges, 2, 2, 1, 3, there's certainly a couple of choices here of some spanning trees that achieve the minimum cost. For example, I could take this one, it would have cost 2, 1, but I could also take this one. So let's call this T1, T2. Both have cost achieving the minimum. Which is 3. Okay. But you notice, for example, I mean, like this choice would not be minimum. That would be 4. And this choice would be 5. So, okay. All right. So, as I said, the weird thing about this particular topic is that there's multiple greedy algorithms that work that are fast and greedy. So let's talk about this. There's a surprisingly simple and fast greedy algorithm that works. I'll explain what I mean by greedy. I should make it clear what I'm writing. Greedy algorithm that always works. So this one is named after someone named Kruskal. Kruskal's greedy algorithm. There's another famous one called Prim's greedy algorithm that's slightly different. I can't spell algorithm. Okay, and so what does it say to do? It says, you want to build yourself this minimum cost spanning tree connecting the vertices? We're just going to build it up as like a bunch of forests that have more and more edges. We're going to add in edges one at a time, starting with no edges, starting with an empty forest. So start with an empty forest. F0 that has 0 edges. And at each step, you're going to add an edge. You just add the cheapest edge that you can to the edges that you've already got in your forest, maintaining that it's a forest, that it has no cycles. Yep, I wrote add the cheapest edge I, add the cheapest edge E to Fi, the forest that you've got so far that has I edges, so that when you add it, the new thing, Fi plus 1, where you add in that edge, sorry, getting a little messy here, Fi union, this new edge, is still a forest. You didn't create any cycles. And what do? You just stop when you got the correct number of edges in your forest. That is when it's a tree. That is when it's the number of vertices minus 1. Sorry. Giving us a spanning tree. Yeah, I don't know. Let me call this thing the greedy tree, the one produced by Kruskal's algorithm. A spanning tree. Okay, so let's do this algorithm. Let's just try it so we can see what we're talking about. Example. I don't know, let's take this one that we had before where there was more than one choice. Those edge costs, a 1, a 2, a 2, and a 3. And then what do we got? We got F0, F1, and F2. So F0 is just going to have no edges at all. F1 says pick the cheapest edge that you can add in to F0 that doesn't create any cycles. Well, not much choice. There's somebody whose cost is 1, and no, there's not 2 things with cost 1, so that's your cheapest. And then F2 says, okay, I got this F1, let me add in one of these edges that I don't already have that doesn't create a cycle, and that's cheapest with that property. I could take this one, or I could take this one. So it's not unique, but that's okay, just pick one. Either this one, oh, that was too much. Either this one or this one. And so there's choices in Kruskal's algorithm, but the claim is it doesn't matter which one you do, you're going to get a minimum cost spanning tree no matter which choices you make along the way. Sound reasonable? Okay, let's try another one. Let me draw a little more complicated graph. This time I think I'll just draw the spanning tree by coloring some of the edges as we go along. Okay, so here's the edges. Let me put on some costs here. Let's make the costs in blue. I don't know. Let's make this one. Let's see. Okay, it's going to go 2, 2, 4, 5, 1. I'm just making sure I don't make a mistake by, I'm going to reproduce what I have in my notes. 5, 1, 3, 3, 4. Okay, what I'm going to do is, let me in another color say I'll just say who we pick first, second, third, and so on. I'll just write, as we take them and mark them in red. So who should we take first? Tell you what, let me label the vertices with some names. That's vertex. Let's try this again. That's vertex A, B, C, D, E, F, G. Okay, let's see. Rebecca, put in the chat. Give me the first edge I should take, or a first edge I could take. The edges, you got to tell me who their endpoints are. So for example, like this edge from here to here is BC. What'd you say? G3. G. Wow. Sorry, Rebecca. You can if you're able to unmute, feel free to unmute.
Yeah, FB.
FB. Okay, but that's not the cheapest. So I'm supposed to take a cheapest one that does not create any cycles with what I've already got. And at the moment, I've got nothing. Right? At the moment, I've just got a whole bunch of isolated vertices. There are no edges at all. Who should I take? Yeah, so just take anybody who's cheapest, right? These are ones, not sevens. I think some people can't read sorry. I do a very ornate looking one, pardon me. But these are the cheapest edges around, are the ones. So it doesn't matter which one you take.
BA then.
Yeah, let's take BA. That doesn't matter. All right. Good. Next, who should I take next? You can keep going, Rebecca.
EA.
EA. Yeah, that'll work. Okay, good. You want to keep going?
AD.
I could take AD.
Oh, sorry, ED.
ED, yeah, I think ED is better because it's cheaper. Yeah, what about, I'll have you go one more step. Tell me who to take next.
AD.
What did you say, AD?
Yeah.
Now, the only problem with that is that would create a cycle. Whoops, I was trying to do my pointer. That would make a cycle. If I add in AD.
Okay, then EF.
EF, yeah, that works. All right, so that was the first time where we didn't have a complete freedom about picking cheapest. We couldn't take this one because even though it's the cheapest value remaining, we're not allowed to make a cycle. Yeah, so what can we do next? Let's think about it. Among the edges that don't create a cycle, there's like this one and this one. I see a 4, a 5, a 5, a 4, 3. Yeah, but I can't take this. I can't take this 2. I can't take this 2. I think 3 is the cheapest thing I can do. Do we believe it? Did I make a mistake? Okay, so the cost of our T greedy here is, what is it? It is 3 plus 2 plus 1 plus 1 plus 1. Is that right? Theo, you're saying wait. Yeah, what's up, Theo? Something bothering you? What about C? Oh, yeah, we haven't connected everybody yet. Good point. We're not done with the algorithm. Wasn't connected. Yeah, and I agree. We have no choice, right? In order to connect to C at this last stage, I missed a step. It would either be this edge or this edge or this edge. But yeah, any one of them would work in terms of not creating a cycle, but this one's the cheapest. So sorry, let me choose that one in T greedy. Let me add the 4 and let me change my 8 to a 12. Did I get that right? All right, billions of things in the chat. Let me just make sure there wasn't anything else. Okay. All right, so questions about how the algorithm runs. You know, and it's not 100% obvious that this is going to work. You know, you can see if the graph was much bigger and you're trying to choose this minimum cost spanning tree, there are a lot of choices about what you might do at each stage. How do we know this sum in the end is always going to achieve the minimum, right? There is a minimum value for the cost of spanning trees. This always will find one of that cost. All right, so that's the theorem. We're asserting, whoa, that looks very thick. How did that get so thick? Did I thicken the? Right.
Are you zoomed in?
I don't know. Oh, maybe I'm, hold on. I think it's because my page was expanded. Now it doesn't look so thick. Good. Ah, here. Oh, that just looks terrible. There, still looks thick, doesn't it? I'm upset about it. Yeah, because I changed the thickness there. There,
You can select it and then change the thickness through that, right? Like you can.
yeah, exactly. That's what happened. So Kruskal's algorithm always produces a minimum spanning tree. Produces that achieves the minimum cost. And so, you know, as usual, I'm bumping up against the time limit for class. So we'll prove this next time. It's not that hard to prove. It's just, it sort of uses some interesting ideas. And then I'll show you an example of another problem where you at least get a reasonable algorithm by starting with the Kruskal algorithm for minimum cost spanning tree. So we'll talk about the traveling salesperson problem and how it relates to this, again, difficult problem of deciding which graphs have a Hamiltonian cycle. And we'll see that Kruskal is an interesting input for traveling salesperson algorithm. So let me see, there's one question in the chat here. Oh yeah, no, that was not a question. Good. So any questions before we turn off the recording and then move into office hour period? All right, any homework type questions that people want on the recording? All right, recording.